Welcome to this session on drilling mechanics and shock and vibrations. In this final submodule 4 of 4, we will examine how drilling parameters, bit selection, well design, and operating practices influence vibration and fatigue. Our focus will be on understanding both proactive and reactive measures to minimize shocks and extend drill string life. In this submodule, we have 5 key learning objectives. First, we will look at how bit selection impacts the development of shocks and vibrations in the wellbore. Second, we'll examine well design practices that help reduce side forces and minimize tortuosity. Third, we'll review equipment settings, particularly related to rotating systems like top drives and rotary tables, that influence torsional response. Fourth, we'll identify operational factors that contribute to drill string fatigue, including practices such as reaming and hole cleaning. Finally, we will bring these points together by considering both proactive and reactive measures that can be applied in the field to control vibrations. By the end of this session, you should have a solid framework for managing vibration in drilling operations. When we talk about fixed cutter bits, particularly PDC bits, their cutting action is driven by torque. To fail the rock, the required stress must exceed the torque applied at the bit. If the torque isn't sufficient, the bit stalls and rotation stops. This is why less aggressive bits, or bits designed for a lower depth of cut, are less prone to stick slip. However, the trade-off is that they remove less rock per revolution, which lowers drilling efficiency. Another factor to consider is the reaction forces generated by the bit. Every cutting action creates an equal and opposite reaction. In the case of PDC bits, this often means that high side cutting forces can cause whirl, where the bit moves eccentrically instead of rotating smoothly. Longer gauge bits can help reduce this risk as they distribute stresses more evenly along the gauge and promote directional stability. This in turn lowers tortuosity in the wellbore. Overall, fixed cutter bit selection involves balancing aggressiveness, depth of cut, and gauge length to optimize performance while minimizing shock and vibration. With that foundation, let's move to how improvements in fixed cutter technology have enhanced bit stability.
The axe blade ridge diamond element bit increases ROP and steerability through increased cutting efficiency and superior frontal impact resistance. The key to the bit's performance is a more aggressive ridge-shaped cutting element that crushes and shears to fail rock more effectively, while its thicker diamond table improves durability. The resulting bit reduces drilling time in a wide range of applications. In laboratory testing, an axe ridge diamond element was tested against a conventional PDC cutter on a granite test block. Under the same drilling conditions, the axe element removed more rock by achieving 22% deeper penetration and generating wider grooves. Finite element analysis simulation further demonstrated the axe blade bit's superior cutting efficiency. In addition, the thicker diamond table on the ridge enables the axe blade bit to achieve better frontal impact resistance to sustain high ROP throughout the run. The axe blade bit enhances trajectory control in directional applications by reducing torque at the bit for maximum production zone exposure. Torque simulations in the IDEA's integrated dynamic design and analysis platform show that the bit generates less overall torque with fewer reactive torque fluctuations for improved steering and ROP. In a wide range of applications, the axe blade bit increases ROP and steerability through increased cutting efficiency and superior frontal impact resistance.
Roller cone bits behave differently from fixed cutters when it comes to vibration. One advantage is that they are generally less prone to generating stick slip at the bit itself. The rolling action of the cones absorbs some of the torsional fluctuations that would otherwise translate into vibration. However, roller cone bits are more susceptible to axial shocks. These occur when the bit bounces vertically under load, which can cause interference in the cones and overload the bearings. Over time, cross-loading, the variation of axial forces across the cones, leads to uneven wear and early bearing failure. Another issue is the mismatch between bit type and formation. When soft formation roller cones are run in harder rock, the cones cannot cut effectively. This mismatch creates frequent axial shocks, further accelerating bearing wear. Once bearings degrade, torsional vibrations quickly increase because the cones no longer rotate smoothly. In short, while roller cones avoid some of the torsional stick-slip problems seen with PDCs, they introduce other risks, particularly axial loading and bearing failure. Careful bit selection and operating parameter control are essential to prevent these outcomes. Next, we'll expand the discussion to well design and how planning influences vibration. Well design plays a critical role in controlling shock and vibration before the bit ever touches rock. The primary principle is designing outside forces by minimizing tortuosity in the planned trajectory. The straighter the weld bore, the fewer contact points there are between the drill string and the borehole wall, which directly reduces vibration and tool wear. However, in modern directional drilling, particularly geosteering, tortuosity cannot always be eliminated. This requires trade-offs between staying in the reservoir target and managing vibration risks. Another important factor is friction. Reducing torque and drag improves the drill string's ability to move smoothly through the well. Friction is influenced by bottom hole assembly design. For example, hard banding can reduce wear at contact points. The mud system also matters. Water-based muds generally provide higher friction, while polymer and oil-based systems reduce it. Adding lubricants can further minimize friction, but their effectiveness depends on the base mud type. In summary, thoughtful well design, considering tortuosity, friction, mud properties, and assembly features, allows us to proactively minimize shock and vibration before drilling begins. With design principles established, we can now turn to how rotating equipment settings influence torsional response. Rotating equipment settings can have a major influence on torsional vibrations. When operating at high RPM, torque output from top drives and rotary tables decreases because the system shifts into high gear. While this provides faster rotation, the lower torque capacity can limit performance in harder formations. Another factor is torque limiters. If they are set too conservatively, they restrict available torque and may cause premature stalls or unstable drilling response. Variability between different power systems also comes into play. For example, SCR-driven systems may produce different power characteristics compared to top drives. Modern soft torque systems and torque feedback controls have been developed to smooth out torsional vibrations. These systems automatically adjust torque in response to fluctuations, helping dampen vibration. However, they must be carefully monitored. In some cases, unintended negative effects have been reported, particularly with earlier generations of technology. Historically, such systems were only available on DC-powered top drives, but now they are increasingly standard across fleets. The key takeaway is that equipment settings, RPM, torque limiters, and torque management systems directly affect vibration behavior. Optimizing these parameters ensures smoother operation. Next, we'll explore other operational factors that also contribute to vibration. Beyond bit selection, well design, and equipment settings, there are a number of operational factors that can trigger or worsen vibrations. Reaming, for example, often creates sudden acceleration changes that introduce torsional and axial shocks. Drilling inside casing, where cement plugs or restrictions are encountered, can also produce abrupt loading. Hole cleaning is another significant contributor. If cuttings are not adequately transported, they accumulate and bind around stabilizers, increasing friction and creating erratic torque response. Poorly stabilized assemblies further exacerbate this by allowing lateral movement of the string. Bi-center drill bits, which are inherently unbalanced in geometry, also increase vibration risk. Finally, bit balling is a classic source of dysfunction. When formation material packs around the cutters, the bit's cutting action is disrupted, leading to stick slip and axial shocks. Each of these factors represents an operational risk that can be managed through proper practices, whether by monitoring hole cleaning, avoiding unnecessary reaming, or using appropriate assemblies. With these contributors understood, let's now examine how shocks and vibrations directly increase drill string fatigue. Fatigue is the leading cause of drill stem failure, and shocks and vibrations significantly accelerate that process. Dynamic motion during vibration cycles the drill string through tensile and torsional stresses. This repeated loading weakens the steel over time, even if the applied stress is below yield strength. Vibration also bends the drill string axially and torsionally, creating additional side forces. Each bending cycle adds to the cumulative fatigue damage. At the same time, short bursts of vibration temporarily increase applied stresses on connections and components, pushing them closer to their fatigue limit. Wear is another outcome. When shocks occur, components such as stabilizers, jars, and drill collars experience accelerated surface damage. This reduces service life and raises the chance of catastrophic failure. For these reasons, harsh drilling environments where shocks and vibrations are common require proactive inspection programs. By regularly checking for fatigue cracks or early wear, operators can remove compromised components before failure occurs. In summary, vibration doesn't just reduce efficiency, it directly shortens drill string life. That is why fatigue management must remain a key focus of drilling optimization. Next, we'll summarize the overall impact of shocks and vibrations on drilling performance. To summarize, shocks and vibrations are universally negative in the drilling process. They directly cause equipment failure by overstressing drill string components and accelerating fatigue. They also consume energy that would otherwise go into rock cutting, which reduces efficiency and increases costs. Another consequence is the effect on well bore quality. Excessive vibration leads to tortuosity and rugosity, making the well bore harder to drill and more challenging to complete. This creates long-term implications for casing running, cementing, and production. The approach to control must be both reactive and proactive. Reactive measures include adjusting drilling parameters in real time to minimize shocks. For example, lifting off bottom to release stored energy, then changing weight on bit or RPM before resuming drilling. Proactive measures involve engineering the well and drill string to minimize the likelihood of vibration in the first place. This includes proper bit selection, optimized BHA design, appropriate stabilizer placement, and careful well planning. Together, these strategies form a comprehensive vibration management approach. By combining real-time adjustments with smart engineering design, we can reduce failures, extend equipment life, and maximize drilling efficiency. With that summary in mind, we'll move into a review of our original learning objectives. Let's take a moment to review the learning objectives we set at the beginning of this sub-module. First, we set out to understand the impact of bit selection on shocks and vibrations. We explored both PDC and roller cone bits, highlighting how each design influences stick slip, whirl, and axial loading. Second, we examined well-designed practices that minimize side forces. We discussed tortuosity, friction, and mud system choices, and how each factor affects vibration. Third, we evaluated equipment settings that shape torsional response. We looked at RPM, torque limiters, and modern soft torque systems that manage fluctuations in power delivery. Fourth, we identified operational factors contributing to drill string fatigue, from reaming and hole cleaning to poor stabilization and bit balling. Finally, we applied both proactive and reactive measures to vibration control, reinforcing the need for real-time parameter adjustment as well as engineered design. Together, these objectives provide a structured framework for managing shocks and vibrations across the drilling process. This brings us to the conclusion of the sub-module. This concludes sub-module 4 of 4 on drilling mechanics, shock and vibrations. You've now seen how bit design, well planning, equipment settings and operational practices all interact to influence vibration and fatigue. Please proceed to the quiz to test your understanding, and thank you for your time and attention.